Hello everyone, and welcome to our presentation. We hope that you're all doing well in these difficult times. We are Team 4, and today we'll be presenting Solit, our solar-powered LED path light. Here's the outline for our presentation, starting with our project motivation. We will then move on to the mechanical and electrical design aspects of our project, followed by physical product testing and our Excel simulation. Lastly, we'll be discussing areas where our project could be further developed.
The goal of this project was to design a self-sustaining light fixture that is free from the power grid. We wanted to design something that could provide light in a sustainable way and provide a solution for a light source in remote areas. There are a few solar-powered streetlights on the current market. However, what makes ours different from the rest is our adaptive system. The adaptive system we created can change the solar panel's angle to the sun in order to maximize the solar energy generation, resultingly increasing the time the light can stay on for. We intended for this light to be used as a path light more than a street light, so the components that we chose as well as the design reflect this intention. With our project, we decided to build the top part of the light and virtually design the rest of the pole due to cost and manufacturing constraints. Our design was inspired by various street poles, and we tried to minimize the air resistance by using as many curved surfaces as possible. Most of our manufactured components are made out of aluminum and are hollow to provide spaces to run the wiring, such as the head of the light and the pole itself. In terms of waterproofing, all metal-to-metal connections are welded together, and any other gaps that we have will be covered using epoxy. The support for the pole is much like other street poles, and we designed it to include space for the battery as well as a hatch for easy access.
A major component of our project is the adaptive solar panel system. Since solar panel efficiency has natural limitations, it is important to optimize energy intake and generation. For our design, we used linear actuators to alter the angle of the panel, both due to availability and ease of use. By positioning the actuator closer to the fixed pole, we produce a large change in angle with a small extension or retraction, while also minimizing energy expended. This function helps us track the sun. We used a ball joint to connect the actuators to the panel. Encased in the slot in the panel bracket, the ball joint slides, allowing the panel to move freely as the actuator adjusts, giving us a wide range of motion. This is especially helpful as we implemented a secondary hinge, providing a second degree of freedom in the lateral direction. With holes in the upper pin, the lateral angle can be adjusted and set upon installation, and is then secured by an L-pin. This helps for implementation on paths in all directions as the panel is more directed towards the sun. As for the programming of the mechanism, we used an H-bridge controlled by an Arduino board to control the movements of the actuator shaft. To essentially follow the sun, we have it set to intermittently extend or retract a small specified displacement every half hour throughout the day, then return to its original position at the end of the day. This can also be adjusted to account for seasonal changes. As a result of our system, we effectively increase our energy intake by approximately 14% in comparison to a stationary solar panel.
Firstly, the solar panel was a vital decision in our project. We researched many options and decided that the 50-watt monocrystalline panel would suit our needs based on our calculations since it optimized cost and performance. Unfortunately, we never had the chance to test the panel, but based on our calculations, these are approximately the results we would anticipate for varying weather conditions and times of the year. Another notable characteristic is that when using solar panels, you need to adjust the power output so it is optimized for your battery conditions. If we were to connect the panel directly to the battery, we would reduce our efficiency by approximately 35%, since the battery and panel are spec'd at different voltages. As a result, we implemented a maximum power point tracking functionality. The circuit on the left shows how. We used the buck converter, which is a DC-DC power converter that steps down the voltage. To adjust the power in the battery, we adjust the voltage using a PWM. Essentially, in the algorithm, you increment the voltage given until the program detects a slight drop in power, as shown on the green curve on the right. Once the drop is detected, it means you have gone past the peak, and then we adjust the PWM to decrease the voltage again. After you have found this peak, you continually adjust to hover around that optimal voltage point, and we implemented this using an Arduino. This method keeps the efficiency around 90%, and while decent, could be much better, and we would improve upon this in further developments of our project.
The LED light is one of the main limiting factors in this project along with weather, as it determines the rate of power loss for our system. We chose the light power output based on similar commercial pathway lights, which generally have a 30-watt output. To save energy, we have incorporated a motion sensing and dimming system to decrease unnecessary power usage while keeping functionality. We had planned to record data of pathway traffic to determine a reasonable estimate for dimming, but due to distancing constraints, we have assumed 3 hours of foot traffic per night. Due to cost limitations and ease, we bought a pre-made LED waterproof light with a built-in housing and reflector. This schematic describes the circuitry connections for the overall system. Because we based our light from a pre-made module, we needed to replace the AC power supply with a DC power controller and add a voltage booster. This was implemented using a high-powered MOSFET and an Arduino. The Arduino is also used to monitor the battery power using a voltage divider. The solar panel control would use a similar MOSFET circuit to prevent the battery from overcharging. The Arduino code is fairly straightforward. Pulse width modulation is used to convert the high voltage from the supply to a desired voltage using the MOSFET. There will be a light sensor monitoring for daylight to activate and deactivate the light, and the motion sensor will control the dimming. The overall power draw of the lighting system is 48 watts. Here is the circuitry system we completed using a temporary switch and power supply, as we could not complete the dimming and the Arduino needs a voltage regulator to be powered from the lead-acid battery. On the left is the voltage booster and on the right is the MOSFET circuit.
Another aspect of our project is the battery, since it stores the energy which comes from the solar panel. When determining the specifications of the battery we needed, we used an Excel simulation to account for varying weather. Based on this simulation, we found that 40 amp hours was the suitable capacity due to weather variance and also so that enough energy could be stored for several nights. After further research, we bought two 12-volt 20 amp hour lead acid batteries due to cost restraints. We put these two batteries in parallel to give us 40 amp hours total. We also designed a battery management system to prevent overcharging and over-discharging. The battery management system was designed using a MOSFET and Arduino and stops the voltage from charging when it reads that the batteries are at 100% and stops discharging when it is at 20%. You can also see from our CAD model that we decided to place the batteries at the bottom of the light pole to maximize space and weatherproof them. Originally, we had planned to test our product outside for a few days to collect data, but we were unable to do so because of the circumstances. To do this, we would have checked each part of the product. First, we would have tested the panel by leaving it out for a wide time range to collect data using Arduino and store it into an SD card. As a part of this test, we would have compared the solar energy gained with and without the adaptive system. We also would have tested the battery to see if the capacity was enough to store the energy from the panel. First, we would try to overcharge the battery with our BMS implemented and check this. We would then test to make sure that the battery stopped supplying voltage at the right point when we were discharging. Using both these test results, we could compare it to our theoretical simulation and adjust our expectations from there. We have already tested our dimming function, and from the pictures above, you can see that it is fully functional. However, our motion sensors did not arrive in time, so we did not get to integrate them with the dimming function. Finally, we would have put everything together and tested how it all functioned. We would have left it out for a range of time and observed it to see if all of its functions work together. As a substitute for testing, we developed a year-long Excel simulation which will be further elaborated on.
To test the year-round validity and robustness of our design, we developed a 1-year simulation on Excel. The simulation takes the specs of the solar panel, light, and battery as parameters, and calculates how much energy the solar panel can absorb, as well as how much power the light uses each night. The calculations for both of these values takes into consideration the daylight hours and cloud coverage of each day based on randomized weather data for Vancouver from 2019. The results on this slide has the light on full power for 3 hours each night in order to account for foot traffic during nighttime hours. The simulation is set up so the battery cuts off at 20% capacity in order to avoid the damage from draining the battery completely. To check for robustness, the weather was randomized for each trial, giving us a result of 75 to 95 nights without enough power. The simulation showed that it would be difficult for our system to work continuously during the fall and winter in Vancouver because of the low daylight hours and cloudy weather. For the light to stay charged for the whole year, we would need a solar panel with 60% efficiency, which is currently unfeasible with modern solar panel technology. Regardless, our current system works well in the spring and summer, being able to provide energy without running out of charge during those seasons.
Finally, we will use the opportunity to reflect on things we would do with more time or resources. Firstly, we would try to find a way to have more degrees of freedom for our adaptive system by adding a rotating base or another actuator. Secondly, we would look to increase the solar energy efficiency by both improving our maximum power point tracking and the panel itself, and as mentioned, an improved adaptive system. Thirdly, we would look to improve our weather resistance. As mentioned, we had waterproofed our design, but we would look to make it so that it can endure cold temperature effects such as freezing, snow, or icicles. And lastly, we might try to add a convex light bulb cover so that the light refracts and spreads further.